In this lecture, we're going to have a look at the area of air traffic management, more well known as air traffic control, even though that's officially only a part of it, but air traffic control and what this can do for a more sustainable flight. But we first have to look then at how today's flights look. Today we have two flights typically, the VFR flight and the IFR flight. VFR flight is where the pilot with his eyes is responsible for visual navigation and visual separation of the other aircraft. Typically general aviation aircraft use VFR flights. But most commercial flights actually follow an IFR flight plan with instrument flight rules, where they follow radio beacons or satellites to navigate, and they have air traffic control taking care of the separation with other aircraft. From the side view, a normal flight of an airliner looks like this. Not a climb to a cruise level and then a descent to the runway, but actually all kind of steps in between. Level segments during climb and descent, and a climbing segments during the level cruise. And this is for air traffic control, and this is also where potentially there are areas for improvement. If we look at the airspaces, then there are different sectors and they have different ways to control the aircraft. En route, having the aircraft at separate levels makes it easier to keep them separated. Closer to the airport, the air traffic controller has to make a sequence of the aircraft before they land on the runway, and the level segments help him in organizing the traffic and sequencing the aircraft until they follow a sort of train flying towards the runway. To keep them separated, air traffic controllers do not watch out of the windows. This is typically only done in tower control for taxiing and for landing and takeoff. But most of the time, the air traffic controllers watch the aircraft on a radar screen, and there's also a digital connection that allows them to know the altitude and even some more information, the identification and some other information of this aircraft. Aircraft fly over airways nowadays, conventional routes, even though there are certain airspaces where they are allowed to take small direct tubes and fly more direct and sort of free route airspace. They don't have to follow these airways, but still, most of the time, aircraft will follow these airways. And if we look at the intersection of the airways, we see radio beacons. In the old days, aircraft needed radio beacons to navigate, so by default they flew from beacon to beacon, and they used position reports over these beacons to tell air traffic control where they were, and so that before there was radar, air traffic control could also separate these aircraft by what's called procedural separation. Procedural separation is still used nowadays, for instance, over the ocean, where there is no radar, and they define oceanic tracks every day, depending on weather and winds, and aircraft fly 12 hours of the day in one direction and 12 hours in the other direction, and by position reports and level assignments, air traffic control can keep the aircraft separated. Another example of procedural separation is by having eastbound aircraft fly on an odd track and westbound on an even track, and in this way they can keep them separated. And by having IFR and VFR at different levels, you can also keep them separated. This is another example of having procedural separation, but in this case as a safety net, because this does not replace air traffic control. If we want to change a system like this, we first have to look at what's the goal of the system. Well, the goal of the system is, of course, to transport people or goods with a certain efficiency, provide this capacity of this transport system. But if we look at changes, sometimes it also has to do with the environment or maintaining certain safety. These are all goals of developments in ATM. And by changing things, you can exchange environment for safety, and not flying is not good for capacity, but is safer and cleaner, and sometimes you fly a bit more dangerously for the environment. So you can exchange that. But if we want to make a real change, and not at the expense of the others, but a real step change, we have to look one level deeper and look at how humans use the systems, and look at humans and systems procedures, and changing the procedures or the systems. The problem with air traffic management is that, in a way, it is actually a global system. There are global standards, so you cannot change something only in one country or one airport. And it is currently quite safe, so any change should not risk reducing the safety. And this means that if something's not fully certain, that people tend to say, let's keep it like it is, because it is quite safe. But for sustainability, we still might need to change it, but it still makes it harder. If we want a complete sustainable flight, we would do it differently than we do today. We would taxi electrically, and of course use green electricity for that. Have a continuous climb to high atmosphere to have thin air as quickly as possible, which is good for drag reduction. Thin air has lower drag, and therefore per distance traveled, you are better off. And an optimal route, benefiting from tailwinds, so not always a direct route, but an optimal route. During the cruise, climb a little bit continuously to get to this thinner air, if you can, because due to fuel consumption, you become lighter and you can fly higher. And the descent, like a glider, have idle throttle and do a continuous descent approach. And then again, taxi electrically. This is a blank sheet approach. But how can we change an existing system? Well, there are changes being made already. For instance, we have now performance-based navigation, in which procedures are flown not from beacon to beacon, but they're flown using a certain performance for your navigation of the aircraft. And whether it's from satellites or ground beacons or whatever system, we then have the ability to make procedures independent of location of beacons, and then more efficient. Also, continuous descent approaches are flown already at night, for instance, when it's not very busy. Why is this? Well, every aircraft type has a different drag, and even within the aircraft type, depending on the weight, you have a different relation between flight angle and speed. You can imagine that if you look at a simple slide, when you're heavier, you go faster down the slide, even though the angle is the same. For continuous descent approaches, this means that while normally you have these level segments to aid you in keeping different aircraft types or weights separated, now they will all gradually get closer to each other, making it harder to have one aircraft overtake the other, or to keep them separated. So that's why there is still work to be done before we have high capacity, idle, continuous descent. En route, flying the most optimal, or often this is simply the direct route, means that we would completely forget the airway structure, which of course aids in keeping the aircraft separated. If you look at the left picture, it's easier to separate those aircraft. You only have to watch those crossings. Than in the right picture, where everybody flies their own optimal route. There are ways in which you can still manage the right picture, and there are two options basically here. Provide more automation, because it's too difficult, or decentralize ATC. If you have more automation, the concept that uses that is called 4D trajectory-based operations, 4D TBO, in which we let the computer calculate which trajectory is completely conflict-free for the complete flight, or at least far ahead, and then have this as a contract with the aircraft. And this way we can make a sort of global optimum for the airspace. But there's a problem with that solution. The problem is that you need quite a good predictability, because you don't want to renegotiate every few seconds. And you need to have airlines share the mass, for instance, which is sensitive information. And maybe also how well they want to keep the time that they arrive somewhere. So sharing sensitive information, and because of the long prediction horizon, missing perhaps opportunities for short-term local optimization, benefiting from a tailwind, which violates the original prediction, are some drawbacks of this approach. On the other hand, if we decentralize it completely, then we do allow for this local optimization, and you don't need to share the sensitive information to optimize your own flight. But doesn't this create a chaos in the air? And is this possible for the pilots to do on top of this? You probably would then only have short look ahead times to only react to upcoming conflicts in, say, 5 minutes. But what does this do for the emerging behavior of an airspace? Well, there are a lot of studies looking at which rules of the sky would work, like rules of the road. And if you look at this example, 8 aircraft flying at the same altitude, same speed, there's always a little bit of noise or turbulence or rounding off. There's a small deviation in the center, and one of the rules that they use here is that in one direction they can only move in a way that magnifies this initial deviation. And you see this already separates the aircraft without any central coordination, which you would expect at this bottleneck. Another example of a bottleneck is the wall here, where one aircraft has a conflict with one other aircraft, But as a reaction to using the rules of the sky, a wave-like pattern starts to occur through the wall, creating quite a nice global solution, even though everybody is only taking care of their own trajectory. You see a hole opening in the wall. So research is being done which rules have this beneficial behavior, but the final solution will probably be a synthesis between centralized and decentralized, where en route, conflicts are a local problem which do not affect the flight planning because the deviations are relatively small. But closer to the runway, you have a central scarce resource to manage, narrow airspaces or the runway sequence, which require global central coordination. And therefore, somewhere it has to transition, but where and how is still a topic of research right now. Summarizing, aircraft today often fly in a way which is not optimal from a sustainability point of view. Some changes are being made. We are trying to get them fly more direct when possible and fly in more efficient procedures, but there's still more work to be done. We also want them to be able to fly continuous descent approaches when it's busy. We want them to have allow local optimization, tactical optimization, a continuous cruise climb, and maybe we have to decentralize air traffic control in parts of the airspace to allow this. If we're able to achieve this, then even with today's aircraft, we can fly much more sustainable than we do. There's a lot to be gained by making ATM more sustainable.